Okay, for our second video we're going to be looking at blood typing, and then we'll get back to blood clotting as well. This is kind of an interesting subject, and try to see if we can make it so this makes sense for you. I think once you understand how it all works, it shouldn't be too complicated. The reason that blood typing is important comes down to this idea of blood transfusion, so giving blood from one person to another. So the thing is that, and I'm sure you know this, that you can't just arbitrarily take blood from one person and give it to another, because if the blood doesn't match, then the body will attack the foreign blood, and we call this agglutination. So the red blood cells will clump up, and the immune system will attack them. If red blood cells are clumping up, then they're not going to be able to transport oxygen like they're supposed to. So this is not a good situation for somebody. So doing a blood transfusion doesn't work correctly. If the body doesn't accept it, then you have even more problems. Potentially the person could die from the wrong blood transfusion. So this becomes important for that reason. And so we discovered these, or scientists discovered these blood types in people, and they discovered there's just a couple different types really. And you may or may not know your blood type. I know my blood type because I've given blood before. In some cultures, blood type is more than just something for blood transfusion. For example, in Japan, blood type is seen as a compatibility thing. So when you're looking to see, trying to decide, I guess, if you like somebody or you want to get to know somebody, you may look at their blood type and see if your blood types are compatible, which is an interesting thing. So we have A, B, AB, and O. Those are the blood types that exist. And these blood types are determined by the antigens that you have on your red blood cells. Remember, the antigens are these proteins associated with cells that determine, or kind of give your cell a fingerprint. So my blood type is type B. So what that means is, if you were to take my red blood cells and test them, you can't see these proteins, they're very, very small. But on my red blood cells, I have these B antigens. And when you look at pictures and things like that, often they'll draw them as little triangles, or in this case, we've got circles and cones. So they're saying is a B antigen. So if you were to look at my red blood cells, you'd see these little spikes all over it. Obviously not really, but that's the idea. These antigens are there, we just can't see them. Somebody with A-type blood has A antigens on their red blood cells. So their body knows that their blood type is A, which means that they are not going to produce antibodies. These are antibodies. This is what antibodies look like. If we could see them under a microscope, they're little Y-shaped proteins. And they match up with antigens. Antibodies match up with antigens. So these antibodies here, these are B-type antibodies. These are A-type antibodies. So I have B-type blood, I have B-type antigens. So what that means is my body produces A-type antibodies. I don't produce B-type antibodies, because then my blood would attack my own blood cells. My body would attack my own red blood cells. But I produce antibodies against other blood types, specifically A-type. So if I was to go in for a transfusion and they were to give me A-type blood, the antibodies in my body would attack those red blood cells with the A antigens, and they'd agglutinate and cause all kinds of problems. If you were to give my blood to somebody that has A-type blood, then the same thing. Their B-type antibodies would attack that blood, and it wouldn't do them any good. So there's A-type blood, B-type blood. Then we have AB-type blood. Someone that has AB-type blood, if you see their red blood cell here, you see it has both the cones and the circles. So they have antigens for both. They have both A-type antigens and B-type antigens. So what that means is they don't produce any antibodies. Because if they produce B-type antibodies, they'd attack their own cells. If they produce A-type antibodies, they attack their own. So they don't produce any antibodies against red blood cells. So what that means is that if you were to give them B-type blood, they'd be fine, because they don't have any antibodies to attack it. If you give them A-type blood, they're fine. And you could also give them AB-type blood, and you can give them O-type blood, because O-type blood doesn't have any antigens on it at all. That's the last type of blood here. O blood, which is the most common type of blood, blood type, does not have any antigens, doesn't have and it does not have B. So what that means is that it produces antibodies against both A and B. So if you have O-type blood, you can't receive A-type blood because the A-type antibodies would attack that blood. You can't receive B-type blood. You can't receive AB-type blood because, again, the antibodies are going to attack that. You can receive O-type blood. So if you have O-type blood, that's the only type of blood that you can receive is O-type blood. But, on the other hand, you can give your blood to any blood type because you don't have any antigens. The antibodies are not going to attack the blood, so you can give it to B-type blood, you can give it to A-type, you can give it to AB-type blood. And that's the way this blood typing works. So you have to figure out what your blood type is, and then that determines what type of blood you can receive in a transfusion. So we come up with this idea of what's called a universal donor and a universal recipient. So universal donor is an individual that they can give their blood to any of the blood types. So one of these 4 blood types is universal donor. Do you know which one it is? The answer is O-type blood. And it's a universal donor because it does not have any antigens, so you can give it to any of these individuals, and because there's no antigens, it's not going to attack. It's not going to be attacked by the antibodies. Universal recipient. So there's a blood type that can receive blood from any other blood type. One of these 4. So which one is a universal recipient? The answer is AB-type blood. Because someone with AB-type blood does not produce any antibodies, they can receive O, B, and A, and nothing's going to attack. So they're considered a universal recipient. On the flip side, though, AB-type blood cannot be given to any other blood type except for AB. So they can receive any blood for any blood type, but they cannot give to any blood type but AB. O, on the other hand, can give to any blood type, but they can only receive O. So you see the differences there. So I kind of think of AB-type blood. This is a selfish blood type. You can get blood from anybody, but you can't really give. And O is a very giving, so you can give blood to anybody, but you can't receive from anybody but O. And that's it. That's how blood type works. You just have to match this up. And so if you want to figure out somebody's blood type, what you can do is you can take a little blood sample and you add the antibodies, and if it agglutinates like this is what it would look like. If it clumps up, then you know that they have that blood type. So you take some of that blood, you put in the antibodies, and then see what you end up with. So if you put in A antibodies, and then you took another sample and put in B antibodies, and it clumps in both of them, then you know you have AB type blood. If you take those 2 samples and no clumping happens, then you know you have O type blood. That's it. So if your blood type is A, you can receive A or O. If your type is B, you can receive B or O. AB, you can receive any of them, and O, you can only receive O, as we talked about. Okay, there is one other type of blood typing system that we usually talk about with what we call the AB blood system, and you've heard of this, I'm sure, because generally if you say, okay, what's your blood type, you don't just say B or A, you say B positive or A negative or whatever it might be. So technically, this is called the RH blood. That positive or negative is considered the RH blood type. But generally, we put them together. They're really 2 different systems. There's the ABO system, and then there's the RH system. But we put them together, and so we say, oh, my blood type is B positive. So in the RH blood group, it's the same idea, though. On your red blood cells, you either have what's called the RH antigen, or you don't. If you do have it, they call that positive. If you don't have it, they call that negative. So, and RH negative individuals, so if you don't have that antigen, they make antibodies against the antigen. Okay, so my blood type is B positive. So if you look at that positive, that means that I produce the RH antigen. That means that I don't produce antibodies against the RH antigen because then I attack my own blood. Somebody that has negative type blood, though, they don't have the antigen, and so they do make antibodies. The thing is, though, is they don't make antibodies until they come in contact with that blood type, with the positive blood type. Now, where this becomes important is it's not as important nowadays because they have a workaround, but it used to be that an individual that had negative blood type, if they were to have a baby with somebody that has positive blood type, then their baby would have the potential of being having Rh positive blood. So what that means is then the mom could potentially produce antibodies against the blood of her baby, and then basically her body would start attacking the baby. The interesting thing though is this would only happen in the second pregnancy. So first pregnancy, the mom would come in contact with that blood at some point, and then her body would start building antibodies against that blood type. And so then if she was to have another baby that had the positive blood type, then the antibodies would already be there and it'd start attacking the baby. So this is where this would be dangerous. So first pregnancy, Rh negative mother with an Rh positive fetus is safe. Subsequent pregnancies, then you may get this what's called a hemolytic disease, where the antibodies start attacking the baby. Severe anemia, bilirubin can lead to brain damage or death. So it's very dangerous. But as I said, nowadays it's not as big a deal because we have this workaround. It's an injection. So and one other note. So this used to be why they would do blood typing before you got married. So it used to be before you get a marriage license, they'd make you go get your blood tested so that they know if you're compatible as far as the Rh negative. It doesn't matter if the father is Rh negative. It's only if the mother is Rh negative, because then she has a potential of having a baby that has a different Rh system. So that is positive. So nowadays, though, if they know that the woman is Rh negative, then they give this injection, immunoglobulin injection, and it basically keeps those antibodies from attacking the fetus, and the mom's fine. Nowadays, they don't even care if it's your first pregnancy or second. It doesn't matter. No, because one other thing. So sometimes what would happen is a female would have a woman would have a miscarriage, and so that miscarriage would then cause her body to start producing these antibodies, and so then she'd have her next pregnancy, and the baby. So even though to her it's her first pregnancy, because sometimes you don't even know you had a miscarriage, her body would start attacking the baby. So now it doesn't even matter. So if you have Rh negative blood, they just give you this injection each pregnancy, and then you're good to go. So it's not as big a deal as it used to be. So that's a good thing. A good thing they figured out how to deal with that problem. Okay, so now let's go to blood clotting. We'll talk just briefly about this, and that'll be it for this chapter. Okay. Hemostasis. This is this idea of blood clotting. That's what we're going to focus on now. Platelets or thrombocytes, these are the important part of clotting. Their job in the blood is to clot. Now you got to think this is a very delicate process, because we don't want clots to happen where they shouldn't happen, but we do want clots to happen where they should. If our blood did not clot, then we could quickly lose too much blood, and that could be life-threatening. But on the other hand, if our blood clots when it shouldn't, that can also be life-threatening, because it can plug up vessels, it can plug up the heart or the brain. Vessels go into the heart or the brain and cause a heart attack or cause a stroke, where where organs in our body are not getting the blood supply that they need, and that can be very, very dangerous. Platelets don't last long. They're just fragments of the megakaryocytes that we talked about, and they're part of this clotting process. So let's look at this. So let's say that you cut yourself. Okay, you get a little cut. So the first thing that's going to happen, there's a few steps that happen. The first thing that's going to happen is what's called vascular spasm. So the vessels that are feeding that area are going to contract. And the reason that happens is because we're trying to reduce the amount of blood that's flowing to that area. So they constrict, try to shut off that blood supply. Obviously don't shut off everything, but you shut off that blood supply to that area to try to keep from losing too much blood. And then we release this serotonin, which is going to trigger the clotting pattern to happen. The next thing, these platelets are constantly flowing in our blood. As long as they're flowing, we're good. But if they get stuck on something, if there's pieces of stuff sticking out, and they slow down for whatever reason, they'll start to pack together. So when we have blood, so if you cut yourself, that tissue is going to be jagged, and so as the blood's flowing by that, the platelets are going to start sticking to those jagged edges, and then it's going to start forming a plug. and they adhere to those little fibers and things that are sticking out and produce this plug. The next thing, we're then going to have coagulation at that clot, and this is where clotting factors come in, and they're going to seal up that area and form a scab and all that sort of stuff. Okay, two mechanisms for activation of clot. First is intrinsic mechanisms. So intrinsic means they're within. So clotting factors that are intrinsic in the blood, that means they're always floating around. However, they're not activated. So this happens when you're exposed to broken collagen in a broken blood vessel wall. Then this intrinsic mechanism can occur. Extrinsic mechanism. This is coming from damaged tissue. So this is when you get a cut or something, and the tissue is going to send out a signal, be like, things aren't going well, and so you're going to initiate a clotting factor. Prothrombin activator is what we're trying to get to here, though. So this prothrombin activator is what's going to start this clotting process. The clotting process is very complex. There's all these steps. And I think the reason is because we don't want this to happen when it's not supposed to happen. So we have lots of places where it can stop. We can stop this process before we form clots where they shouldn't form. So here's what's going on. So we have prothrombin activator, and then that converts prothrombin, which is floating around in the blood, to thrombin. And then thrombin then goes and interacts with fibrinogen, which is also floating around in the blood at all times, and it produces fibrin. So prothrombin and fibrinogen are always in the blood, but they're not active. So you need this prothrombin activator to activate prothrombin, and you need prothrombin to become thrombin so it can activate fibrinogen into fibrin. Whoa, tongue twister. And then that's what produces the fibers that wind around the platelet plug, and they trap the red blood cells. That's going to form what we think of as a clot, this clotting process. Hemostasis. There you go, and you can see the cascade here. Vascular spasm, platelet plug formation, and then coagulation. Prothrombin activates prothrombin into thrombin, which then interacts with fibrinogen to form fibrin, and then you get the blood clot. And this, you can see all these fibers holding the red blood cells there. It's a pretty amazing process, and it's good that it happens, and our body's able to heal in these ways. But it can be bad if clots happen where they should not be. So things that can cause unwanted clot formation: undamaged tissue, smooth endothelial lining of blood vessels, anticoagulants in the blood. So as long as you have these, then you shouldn't form clots where you don't want them. Undamaged tissue means everything's nice and smooth. Smooth lining of the blood vessels, everything, so the blood's just able to flow. It's not getting plugged up anywhere. We also produce our own anticoagulants that help this prevent this from happening. However, it can happen. It can happen, and this becomes a problem. First one to mention here is thrombocytopenia. Thrombocytopenia. This is when your platelet count is low, and this can be a problem because you aren't able to clot like you should. You could bruise very easily. Lots of things could be happening, and it can be caused by a lot of different things. Could be inherited. It could be caused by cancer. It could be caused by something keeping the platelets, bone marrow damage or something like that, keeping the platelets from being formed. Hemophilia. Hemophilia is a situation, maybe you've heard of hemophiliacs. Someone that has hemophilia is missing some of the clotting factors. So there's a number, as I said, we just looked at, this is a simplified process of hemostasis. There's a lot of factors. These are the main steps. There's all these factors in place, as many as 10, 12 factors that have to happen in this cascade in order for clotting to happen. If you're missing any of those, then you've got a problem. So somebody that's missing any one of these clotting factors can be a hemophiliac, or it can lead to hemophilia, meaning that their blood does not clot. And obviously this can be very, very dangerous, because if you get a cut, even a simple cut or something like that, then your body can lose a lot of blood. And we don't realize it, but as we're walking around throughout the day, I mean, even if you were to bump a wall or something like that, you may break a little blood vessel or a capillary. You wouldn't even know it because the clotting process happens so quickly inside the vessel you don't lose any blood. That's where somebody with thrombocytopenia, they can bruise easily because they'll bump into something. Instead of that closing up really fast, that blood starts to leak out and they get these bruises and things like that. So hemophilia would be like that, even more extreme. So just bumping around all day long, you'd start getting bruises and get hemorrhages and stuff. So it can be a very deadly disease. Luckily nowadays they can supplement these clotting factors so that these individuals can get the things they need. But if someone has hemophilia, they'll generally wear something like a wristband or dog tags or something. So if they're in an accident or something, then people can see that they have hemophilia. So we need to make sure that we treat that correctly. A thrombus versus an embolus. A thrombus is a blood clot that forms somewhere in the body, and it's there. So some good examples of where you might come in contact with this. When you're flying on a plane, if you're flying for a long time, they recommend that you get up every so often and move around. Because what happens is that as you're sitting there, the blood will start to pool in your feet because you're not up moving around. And as that blood pools in your feet, there's a potential, in your legs and your feet, there's a potential for that blood to slow down to a point that you'll start to form a clot. That's called a thrombus. And then you'll jump up suddenly, and then your blood will start flowing faster, and then that clot, the blood may hit that clot and it break it off, so it's not in place anymore. Thrombus can be dangerous if it's it's kind of impeding the flow in a vessel or something like that. But if it breaks off and starts moving in the circulation, then it becomes an embolus, and then it becomes very, very dangerous because that embolus is going to flow until it gets stuck somewhere, meaning that so as you're going back to the heart, the vessels are getting bigger and bigger and bigger. So if it forms in a vein in your feet, then it breaks off, becomes an embolus. It's moving up towards your heart. The vessel's getting bigger and bigger, so it's not going to get stuck. Then it'll go through your heart, and then go to your lungs, for example. And now the vessels get smaller, smaller, smaller as they go to the lungs. Suddenly it gets stuck, and it blocks the exchange of oxygen in your lungs. Then we call that a pulmonary thromboembolism, and that can be very, very dangerous. That can be life-threatening because you're not getting the oxygen that you need. Or that clot could get stuck in your brain, cerebrovascular accident or a stroke. So it blocks off the vessels, your brain doesn't get the oxygen it needs, and your brain cells start to die very quickly. They can survive. So your brain, after about 3 minutes with no oxygen, starts to break. They start to die, and so then if parts of your brain die, then we call that a stroke. So hemostasis, where it's not supposed to happen, can be very, very dangerous. So that's all we're going to talk about there. Just to mention here, there are a lot of H words now. So we've talked about homeostasis, which is a balance that we're trying to maintain in our body. We've talked about hemostasis, which is blood clotting. And we've also talked about hematopoiesis, which is the formation of the formed elements in the blood. So try to keep all these little H words separate and understand their definitions as you're learning these things. Let me just mention the last thing, the effects of aging. Anemia's increase. You get iron deficiency anemia, pernicious anemia, leukemia increases, then you get clotting disorders that can be caused by the blocking of arteries due to diet, arteriosclerosis, where you get clogging of arteries, can happen. So got to keep diet and exercise a part of your lifestyle as you get older.